Welcome students to this lecture of electrochemistry. In the last lecture, we have discussed the relationship between standard cell potential and equilibrium constant. We have also discussed the standard hydrogen electrode, the construction and the working of the standard hydrogen electrode. The disadvantages also we have discussed. We have also discussed the different types of useful cells in our day-to-day life, that is primary voltaic cell and secondary voltaic cell. In that, we have discussed nickel cadmium cell and hydrogen oxygen electrode. Now, today we'll be discussing the electrochemical series. As you all know, this is a series of elements in which the standard potential of a number of electrodes have been determined using standard hydrogen electrode. These electrodes with their half reactions are arranged according to the decreasing standard potential. So this arrangement is called as electrochemical series. I repeat again, the standard potential of a number of electrodes have been determined using standard hydrogen electrode. These electrodes with their half reactions are arranged according to their decreasing standard potential, and this arrangement is called as electromotive series or EMF series. Now, there are different points to remember in this EMF series. The key points of this EMF series are as follows. The half reactions are written as reduction reactions. The oxidizing agent and electrons appear on the left hand side of the half reaction, while the reducing agents are shown on the right hand side in the half reaction. Next point, below hydrogen, the negative standard potential increases, and above hydrogen electrode, the positive standard potential increases. The E standard values apply to reduction half reactions that occur in forward direction as written. The higher E standard values for half reaction indicates its greater tendency to occur in forward direction, and in turn have a greater tendency for a substance to reduce. Conversely, the low E standard value of half reaction corresponds to its greater tendency to occur in reverse direction, or for a substance to oxidize. The half reactions listed in this order of decreasing tendency in forward direction. So this is a series of elements which has been arranged, and this series of elements are is called as EMF series or electromotive series. So in this series, as you all know, that half reactions are written. The half reactions of the elements which undergo oxidation and reduction have been written. The potentials have been written at the end. As we all know, uh, hydrogen is supposed to be standard, and here the values of hydrogen is taken at 0. The negative values go on increasing as we move down the hydrogen. The positive value go on increasing as we move up in this EMF series. So More positive values of the reaction indicates that there is a forward reaction and there is a reduction type of reaction, and more reverse direction indicates the oxidation reaction. So this is the table for your reference, and this table is used as a reference to understand what is called as electromotive series or EMF series. So here the concentrations are taken, 1 molar concentration reactions are taken into consideration, and the pressure, that is 1 atmosphere pressure, is also taken into consideration. Now, applications of EMF series or electrochemical series. There are 3 to 4 points that I want to discuss regarding the applications of EMF series. EMF series, there are 3 main applications we will discuss: the relative strength of oxidizing agent, the relative strength of reducing agent, and also we will be discussing the spontaneity of the redox reactions. Now, the first point is relative strength of oxidizing agents. The species on the left hand side of the half reactions are oxidizing agents. The E standard values of is a measure of the tendency of the species to accept electron and get reduced. On, in other words, the E standard value measures the strength of the substances as oxidizing agent. Larger the E standard values, greater is the oxidizing strength. The species in the top left side of the half reactions are strong oxidizing agents. As we move down the table in this EMF series, the E standard values and strength of oxidizing agent decreases from top to bottom. So this is the relative strength of the oxidizing agent. The relative strength of the oxidizing agent decreases from top to bottom in the EMF series. Now, the next point is the relative strength of reducing agent. The species on the right side of half reactions are reducing agents. The half reaction at the bottom of the table with large negative E standard values have little or no tendency to occur in the forward direction as written. They tend to favor the reverse direction. It follows that species appearing at the bottom right side of half reaction associated with large negative E standard values are effective electron donors. They serve as strong reducing agents. The strength of the reducing agents increases from top to bottom as E standard values decreases. So this is the second point, that is second application, where relative strength of reducing agent increases from top to bottom as the E standard values decreases. Now the third application, which is called as spontaneity of redox reaction. So in a galvanic cell, the redox reactions spontaneously take place if the species with higher sorry, species with higher E standard value is reduced, and that with lower E standard value is oxidized, the standard cell potential must be positive for cell reaction to be spontaneous. Under standard conditions, noteworthy applications of electromotive series is predicting spontaneity for redox reactions from the knowledge of standard potential. Suppose, as we ask questions, at standard conditions, would Ag plus ions oxidize metallic magnesium? The answer to this question is that we write oxidation of Mg by Ag plus. So, a reaction with the reaction we can explain. So, Mg gives Mg plus 2 electrons. So, Ag plus 2 accepts the electrons and accepts the electrons and it gets reduced to Ag. It gets reduced to Ag. So, the overall reaction is as follows. So Mg plus 2Ag gives Mg2 plus 2Ag plus 2Ag. From the table of electrochemical series, we see that the E standard value of Mg is minus 2.37 and the E standard value of Ag is minus 8 for the cell having Mg as anode and Ag as a cathode. So therefore, the E standard cell is equal to E standard Ag minus E standard Mg, which is equal to 0.8 volt minus into minus 2.37 volt. The answer will be 3.17 volt. So the EMF being positive, the cell reaction is positive. As we have received a positive answer, the cell reaction is spontaneous. Thus, Ag ions can oxidize to metallic Mg. Ag plus ions can oxidize to metallic Mg. The fourth application of EMF series is in calculation of standard cell potential. The E standard cell can be calculated from the electrochemical series, the standard cell potential, that is E cell, from the standard reduction potential values of the half reactions can be calculated. For example, if suppose we have a reaction that is Zn plus 2 electrons gives Zn plus, and the EMF is given as E standard Zn plus 2 upon Zn is equal to minus 0.76 volt. And for the second reaction, Cu plus 2 electrons gives rise to Cu solid. The standard potential is E standard Cu plus 2 upon Cu is equal to minus 0.34 volt. So for the cell reaction, when we write a cell like this, Zn, a single vertical line, Zn plus 2 aqueous solution, 1 molar concentration, double line which indicates the salt bridge, Cu plus 2 aqueous, 1 molar concentration, a single vertical line along with copper. So when we write the EMF of this cell, it will be E standard cell is equal to E standard Cu 2 plus upon Cu minus E standard of Zn 2 plus upon Zn, that is cathode minus anode. So then we substitute the values 3.34 minus into minus 0.76. The answer will be 1.1 volt. The answer will be 1.1 volt. Thus, we can calculate the standard cell potential of a cell by using the EMF series. So with this, we come to an end of this chapter.